The universe is everything that exists. Every star, every planet, every stretch of empty space, and every moment of time are all part of it. Tonight we will move slowly through simple, steady facts about this vast system, not to overwhelm the mind, but to let it settle. Welcome to AstraFlow. Here, science drifts like starlight, and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing soften, and your mind settle into quiet understanding. If you're listening from somewhere familiar, a bedroom, a quiet living room, or a place far from home, you're welcome to share where you are in the comments. If this space helps you rest, a gentle like or subscription supports the channel and keeps these long, quiet explorations flowing. Now, let's begin and explore the science of one relaxing facts about the universe to fall asleep to. When scientists talk about the universe, they are not describing an abstract idea. They mean something very specific. The universe is the total of all space, all time, all matter, and all energy. There's nothing outside of it that we can measure or observe. Every experiment, every observation, and every physical law exists within this single system. This definition matters because it sets a boundary for what science can study. Astronomy and physics do not speculate about places beyond the universe. They focus on what can be observed, measured, and tested. That focus is one reason modern science has been able to describe the universe with such consistency and reliability. The universe is not just a collection of objects floating in emptiness. Space itself is part of the universe. Time itself is part of the universe. Events happen not only in space, but as space changes and stretches. This may sound complex, but the key idea is simple. Everything you experience is happening inside one continuous physical structure. When you look at the night sky, you're not seeing the universe as it is right now. You're seeing light that has travelled for years, centuries, or millions of years before reaching your eyes. This means astronomy is also a study of the past. The farther away something is, the older the light we receive from it. This fact alone explains why studying the universe requires patience. Nothing changes quickly on cosmic scales. Stars take millions of years to form. Galaxies evolve over billions of years. Even dramatic events like the birth or death of a star unfold slowly when measured across time. Because of this, the universe is naturally calm. It is not rushed. It does not react instantly. Processes move forward at steady rates, guided by physical laws that do not change from day to day. Those laws, gravity, motion, energy, and time, apply everywhere we look. They work the same way on Earth as they do in distant galaxies. This consistency is one of the most comforting discoveries in science. It means the universe is predictable, even when it is vast. As we move through these facts tonight, there is no need to remember details or hold on to explanations. You can let each idea pass by slowly, like distant lights moving across the sky. The purpose is not mastery or insight. It is gentle understanding. You're not required to stay alert, you're allowed to drift. The universe will continue its steady motion whether you listen closely or fade into rest. In the next section, we will narrow our focus slightly, from the entire universe to the part we can actually observe. A smaller view, still immense, still calm. When we talk about the universe, it is important to be clear about what we can actually study. Scientists often use a specific term, the observable universe. This does not mean the universe is limited to what we observe. It simply means there is a boundary to what information can reach us. The observable universe is defined by light. light travels at a finite speed. Because of this, there is maximum distance from which light has had enough time to reach Earth since the universe began. Anything farther away than that distance exists beyond our current ability to observe. This boundary is not a physical wall, it is not an edge where the universe stops. It is a horizon created by time and motion. As time passes, this horizon slowly changes, allowing light from more distant regions to reach us. This idea helps explain why astronomy feels both precise and incomplete. We can measure distances, temperatures, and motions with great accuracy. At the same time, we know there is more beyond what we can currently see. Science accepts this limitation calmly, without urgency. The observable universe contains hundreds of billions of galaxies. Each galaxy contains billions, or even trillions of stars. Between those stars are planets, dust, gas, and vast regions of nearly empty space. Even within this observable portion, the scale is difficult to fully imagine. To manage this scale, scientists rely on careful measurement rather than intuition. Distances are calculated using the behavior of light, the motion of objects, and known physical laws. These methods allow astronomers to build maps of space that remain consistent even as new data is added. One important point is that we do not see all objects as they are right now. We see them as they were when the light left them. A galaxy 1 million light-years away is seen as it existed 1 million years ago. A galaxy 10 billion light-years away appears as it was when the universe itself was much younger. This makes the observable universe a kind of historical record. By looking deeper into space, astronomers are also looking deeper into time. This is one reason space observations are so valuable. They allow scientists to test ideas about how the universe has changed. Despite this complexity, the overall picture remains calm and stable. On the larger scales, the universe looks smooth and uniform. Matter is spread out in predictable patterns, shaped by gravity over long periods of time. There is no sense of chaos when viewed broadly. This stability is reassuring. It tells us that the universe is not fragile. It does not depend on constant adjustment or intervention. It follows rules that have held steady for billions of years. As listeners, there is no need to visualize every number or distance. You can simply hold on to the idea that what we see is a portion of a much larger whole. A quiet sample, revealed gradually through light and time. The observable universe is not something we rush to understand. It unfolds slowly, observation by observation. Just as your body naturally slows as you rest, the universe reveals itself at a steady pace. In the next section, we will focus on the one thing that makes observation possible at all: light itself, the universe's primary messenger. Almost everything we know about the universe comes from light. Not from touch, not from sound, but from light travelling across space and reaching our instruments. Light is a form of energy that moves at a constant speed through empty space. In a vacuum, that speed is about 300,000 kilometers per second. This speed is fast by human standards, but on cosmic scales it introduces distance, delay, and patience into every observation. When a star shines, it is sending light outward in all directions. Some of that light eventually reaches planets, telescopes, and detectors. Only when it arrives can information be gathered. Until then, whatever is happening at the source remains unknown to us. This is why astronomers rely so heavily on careful measurement of light. They study its brightness, its colour, its direction, and its timing. From these properties they can determine how hot a star is, how fast it is moving, and even what elements it contains. light changes slightly depending on what produces it. Hot objects emit different wavelengths than cooler ones. Gases absorb and emit specific patterns of light. By learning these patterns, scientists can identify materials without ever touching them. This method may feel indirect, but it is remarkably reliable. The same physical rules that govern light in laboratories on Earth also apply in distant galaxies. Because of this consistency, light becomes a trustworthy messenger. It is also a patient one. Light does not rush. It arrives exactly when physics allows it to arrive, no sooner and no later. This creates a natural rhythm in astronomy. Observe, measure, wait, and refine. There are limits to what light can tell us. Some regions of the universe are hidden by dust. Others emit very little visible light. To address this, astronomers study many forms of light, including radio waves, infrared, ultraviolet, and X-rays. Each type of light reveals a different layer of reality. Together they form a more complete picture, built slowly over time. No single observation is final. Understanding grows through accumulation. For a listener resting quietly, this idea can be grounding. Knowledge does not arrive all at once. It comes in gentle signals, collected piece by piece. The universe does not demand attention. It offers information calmly. As you listen, you do not need to analyze or remember details. You can simply let the idea settle. Light travels, carries information, and arrives when it is ready. In the next part, we will use this understanding of light to explain something very familiar: why stars appear small, even though many of them are larger than our sun. When you look up at the night sky, stars appear as tiny points of light. They seem delicate, distant, and almost flat against the darkness. In reality, many of those stars are enormous, far larger than our sun. The reason stars look small has nothing to do with their actual size. It is almost entirely about distance. Even the closest star beyond our sun is so far away that its vast size becomes compressed into a single point of light by the time it reaches your eyes. This effect is familiar in everyday life. A large mountain looks small when viewed from far away. An airplane high in the sky appears much smaller than a bird nearby. Distance reduces apparent size, even when the object itself is massive. Stars are extreme examples of this effect. They are separated from us by distances so large that ordinary units like kilometers become impractical. Instead, astronomers use light years, the distance light travels in 1 year. Even nearby stars are several light years away. Because of this distance, stars do not appear as disks to the human eye. They appear as points. Only with powerful telescopes can we measure their true size, and even then, it requires careful techniques and indirect methods. Some stars are many times wider than the orbit of Earth around the Sun. Others are smaller, denser, and hotter. But from Earth, distance smooths out these differences into gentle, steady points of light. This has an interesting calming implication. What looks simple may not be simple at all. What looks small may be vast. The universe does not advertise its scale loudly. Astronomy often works by correcting intuition. Our senses evolved for nearby objects and short distances. Science extends those senses carefully, without forcing understanding all at once. You do not need to imagine the full size of a star to appreciate this fact. It is enough to know that appearance is shaped by distance, and distance is common in the universe. Space is mostly separation. As your body rests, this idea can settle gently. Things can be far away and still real. They can be large and still quiet. In the next section, we will talk about time on a cosmic scale, and how scientists estimate the age of the universe itself. One of the most basic questions in astronomy is also one of the calmest. How old is the universe? Current scientific evidence suggests that the universe is about 13.8 billion years old. This number is not guessed. It comes from multiple independent measurements that agree with each other in steady, reliable ways. Scientists estimate the age of the universe by observing how it is expanding. When galaxies move away from each other, their light changes slightly. By measuring this change, astronomers can calculate how far space itself is stretching. Running that expansion backward leads to a time when everything was much closer together. Another source of evidence comes from the oldest light we can detect. This light fills the universe evenly and comes from a very early stage in cosmic history. It provides a kind of timestamp, showing what conditions were like when the universe was young. Importantly, the age of the universe does not refer to a single moment in space. It refers to the amount of time that has passed since the universe began expanding in its current form. Every region we can observe shares this same history. On human timescales, billions of years are impossible to feel. Our lives are measured in decades. History books cover centuries. But the universe operates on much longer timelines, where slow change is normal. This long duration explains why the universe appears stable. Stars have time to form, shine, and fade. Galaxies have time to organize into patterns. Nothing needs to happen quickly. There is no urgency in cosmic time. Processes unfold gradually, guided by physical laws that do not rush. Even dramatic changes, like the formation of stars, take millions of years. You do not need to imagine all 13.8 billion years at once. It is enough to know that the universe has had time to settle into the structures we see. Time on this scale is a stabilizing force. As you rest, this idea can feel grounding. The universe is old, steady, and patient. It does not demand attention or speed. In the next part, we will explore what it means that the universe is still expanding today, slowly and continuously. The universe is not standing still. It is expanding. This does not mean that stars and galaxies are flying outward through space like fragments from an explosion. Instead, the space between galaxies is slowly stretching. As space expands, distant galaxies become farther apart, even though they may not be moving much on their own. This idea can feel abstract, but it's based on careful observation. When astronomers study light from distant galaxies, they notice a consistent pattern. The light is shifted toward longer wavelengths. This shift indicates that space itself has expanded while the light was traveling. The farther away a galaxy is, the stronger this effect appears. This tells scientists that expansion is happening everywhere, not from a central point. There is no center of the universe where expansion began. Every region experiences the same process. The expansion of the universe is slow and steady. On human timescales, it is completely unnoticeable. Galaxies, solar systems, and atoms remain bound by gravity and other forces. Expansion only becomes measurable across enormous distances. This explains why everyday structures are unaffected. Your body, the Earth, and even the Milky Way galaxy are not being pulled apart. Local forces are strong enough to hold them together. Expansion becomes relevant only between vast, unbound regions of space. Scientists describe this expansion with simple mathematical relationships. These relationships allow astronomers to estimate distances, ages, and future behavior. The same equations apply consistently across the observable universe. Importantly, expansion is not chaotic. it follows predictable rules. The universe does not expand faster in some places and slower in others. On large scales, the process is smooth. This smoothness contributes to the universe's overall calm. Despite its size, it behaves in orderly ways. Change happens gradually without sudden shift or instability. For a resting mind, this can be comforting. The universe is active, but not frantic. Motion exists, but it is measured and even. As you listen, you do not need to picture expanding space in detail. You can simply hold the idea that the universe changes slowly, continuously, and without urgency. In the next section, we will look at galaxies themselves, not as distant abstractions, but as organized collections of stars moving together through space. Galaxies are large groups of stars held together by gravity. They are not random collections. They are structured systems that move through space as connected units. A typical galaxy contains billions of stars. Along with those stars are planets, clouds of gas, dust, and regions where new stars are forming. Between these components is a great deal of empty space, but gravity keeps everything loosely bound. Galaxies exist because gravity works over long distances. When matter gathers in one region, gravity pulls nearby material inward. Over time, this slow attraction leads to organized systems rather than scattered objects. The result is a galaxy. You can think of a galaxy as a kind of neighborhood. Stars within a galaxy influence one another gravitationally. They orbit a common center, moving in steady, predictable paths over millions or billions of years. This shared motion is what defines a galaxy as a single structure. There are many types of galaxies, but they all serve the same role. They provide environments where stars can form, evolve, and eventually fade. Without galaxies, matter would be spread too thinly for stars and planets to exist. Galaxies are separated from one another by vast distances. Between them lies intergalactic space, where matter is extremely sparse. This separation makes galaxies distinct systems, rather than parts of one continuous mass. Despite their distance from one another, galaxies are not isolated. They can interact through gravity. Sometimes they pass close together, exchange material, or merge slowly over time. These interactions happen gently on cosmic timescales. Most galaxies have existed for billions of years. Their structures change slowly, shaped by motion and gravity rather than sudden events. Even when galaxies collide, the process unfolds over hundreds of millions of years, giving stars ample time to adjust their paths. For scientists, galaxies are useful units of study. They are large enough to reveal patterns, yet organized enough to be understood as systems. By studying many galaxies, astronomers can learn how matter behaves on the larger scales. For a listener at rest, galaxies can be thought of as stable communities of stars. They are not chaotic or violent by default. They are persistent, long-lasting structures. This idea can settle the mind. The universe builds complexity slowly. It favors organization over disorder when given enough time. You do not need to imagine the full number of stars in a galaxy. It is enough to know that stars rarely exist alone. They are part of larger systems, moving together through space. In the next part, we will narrow our focus further and explore our own galaxy, the Milky Way, and where we are located within it. The Milky Way is the galaxy that contains our solar system. Every star you see in the night sky, without the aid of a telescope, belongs to this single galaxy. When you look upward, you are looking inward, across a vast but connected system. The Milky Way is a spiral galaxy. It has a flattened disk with spiral arms that curve outward from a central region. These arms are not solid structures. They are areas where stars, gas and dust are more concentrated. Our Sun is located in one of these spiral arms, far from the centre of the galaxy. We orbit the galactic centre along with billions of other stars. One complete orbit takes about 225 million years. This means the Sun has made only a small number of trips around the galaxy since it formed. The centre of the Milky Way contains a dense concentration of stars. It also hosts a very massive object that influences the motion of surrounding stars. This central region is crowded, energetic, and very different from our local neighbourhood. Where we are located, conditions are calmer. Stars are spaced relatively far apart. The environment is stable enough for planets to form and persist for long periods of time. This stability has allowed life to develop on Earth. The Milky Way is enormous. It contains hundreds of billions of stars spread across a disk that is about 100,000 light-years wide. Yet even at this scale, the galaxy is thin compared to its width, giving it a flattened shape. Despite its size, the Milky Way moves smoothly. Stars follow predictable orbits shaped by gravity. There is no sense of turbulence or rapid change on short timescales. This regular motion is another example of cosmic calm. Large systems behave in orderly ways when guided by consistent laws. The galaxy does not need constant adjustment to remain stable. As you rest, it can be comforting to remember that you are part of this slow motion. The Earth, the Sun, and everything familiar are quietly orbiting together. Nothing is required of you to keep this motion going. You do not need to picture the entire Milky Way in detail. It is enough to know that it is structured, stable, and long-lasting. A home system moving gently through space. In the next section, we will look at why galaxies, including the Milky Way, have different shapes, and what those shapes tell scientists about motion and gravity. When astronomers observe galaxies, one of the first things they notice is shape. Some galaxies appear as flat spirals, others look rounder and smoother. Some have no clear structure at all. These shapes are not decorative. They are the result of motion, gravity, and time working together. Spiral galaxies like the Milky Way form when large amounts of matter rotate around a central region. As stars and gas orbit, their motion flattens the system into a disk. Over long periods, regions of higher density appear as spiral arms. These arms are patterns of motion, not fixed structures. Elliptical galaxies look very different. They are more rounded and lack clear spiral features. In these galaxies, stars move in many different directions rather than following a shared rotation. This kind of motion produces a smoother, more uniform shape. Irregular galaxies have no clear form at all. They often result from interactions between galaxies. Gravitational encounters can stretch, compress, or disrupt structure, leaving behind uneven shapes. Even so, these systems still obey the same physical laws. Galaxy shape tells scientists about history. A well-defined spiral suggests long-term stability and steady rotation. A distorted or irregular shape suggests past interactions or mergers. By studying shape, astronomers learn what a galaxy has experienced over billions of years. Importantly, these changes happen slowly. A galaxy does not suddenly change shape. The process unfolds over immense timescales, allowing stars to adjust gradually to new paths. This slow evolution is another sign of cosmic calm. Even large-scale transformations are not abrupt. The universe favours gradual adjustment over sudden change. For a resting listener, galaxy shapes can be thought of as records rather than events. They show motion frozen into form. They reflect balance rather than conflict. You do not need to remember the categories or names. It is enough to know that shape arises from motion, and motion follows simple rules. Gravity organizes matter patiently. As you breathe and settle, this idea can remain in the background. Large systems find their form naturally over time. They do not rush. In the next part, we will focus on the force responsible for this organization, gravity, and how it quietly shapes everything from galaxies to planets. Gravity is the force that gives structure to the universe. It is always present, always active, and yet often unnoticed. Unlike other forces, gravity does not switch off. It works quietly, over long distances, shaping matter wherever it exists. At its simplest, gravity is an attraction between masses. Anything with mass pulls on anything else with mass. The more mass an object has, the stronger its gravitational pull. The closer objects are to each other, the stronger that pull becomes. On Earth, gravity feels constant and familiar. It keeps us grounded. It shapes the motion of water, air, and falling objects. In space, the same force operates, but its effects are easier to see on large scales. Gravity pulls gas and dust together to form stars. It holds planets in orbit around those stars. It binds stars into galaxies and galaxies into larger groups. Without gravity, matter would drift apart and complex structures would not form. One reason gravity is so effective is that it works over vast distances. Light can travel across empty space, but gravity reaches across it as well. Even when matter is spread thinly, gravity still acts, slowly drawing material together. This action is not sudden. Gravity rarely causes instant change. Instead, it produces gradual motion. Objects fall, orbit, or settle into balance over time. Because of this, gravity creates stability. Planets remain in their paths. Stars stay bound within galaxies. Systems persist for millions or billions of years. Gravity also allows motion without collision. Objects can orbit without touching. This balance between attraction and movement is what keeps systems organized rather than collapsing inward. For scientists, gravity provides a unifying explanation. The same equations describe falling objects on Earth and orbiting galaxies far away. This consistency makes gravity one of the most reliable tools for understanding the universe. For someone resting, gravity can be thought of as a steady presence. It does not demand attention. It does not change unpredictably. It simply works. As you lie still, gravity is supporting you. It holds the Earth together. It keeps the planet in orbit. It connects everything quietly. You do not need to imagine gravity pulling or stretching space. You can let it remain a background force, steady and dependable. In the next section, we will look at one of gravity's gentlest outcomes, the slow and careful birth of stars within clouds of gas and dust. Stars begin their lives quietly. They do not appear suddenly or dramatically. They form slowly, over long periods of time inside large clouds of gas and dust. These clouds are called molecular clouds. They are cold, dark regions of space where atoms and molecules move gently. Most of the time, nothing noticeable happens inside them. They can remain stable for millions of years. Star formation begins when gravity slowly changes the balance. A small region within a cloud may become slightly denser than its surroundings. This can happen due to gentle disturbances, such as the motion of nearby material or the influence of a passing shock wave. Once a region becomes dense enough, gravity begins to pull it inward. As the material gathers, it forms a clump. That clump continues to attract more gas and dust from the surrounding cloud. Over time, the clump grows heavier and warmer. This process is gradual and unhurried. As the material falls inward, it begins to rotate slowly. This rotation causes the forming star to flatten slightly, with a disk of material around it. Some of this material may later form planets, but at this stage, the focus is the star itself. Eventually, the center of the clump becomes hot and dense enough for nuclear reactions to begin. When this happens, a star is born. It starts producing energy in its core and begins to shine. This moment marks the transition from a cloud of gas to a stable star. Even then, the process is not instant. A newly formed star takes time to settle into balance. It adjusts its temperature, size, and energy output gradually. Only after this settling does it enter a long, stable phase of its life. Star formation explains why galaxies are not static. They continue to produce new stars even billions of years after they formed. This slow renewal keeps galaxies active without causing disruption. For a resting mind, this process can feel reassuring. Stars do not rush into existence. They form when conditions allow, and only after long preparation. You do not need to imagine every step or detail. It is enough to know that stars are not sudden events. They are the result of patience, gravity, and time working together. As you rest, this idea can mirror your own stillness. Nothing needs to happen quickly. Change can wait. In the next section, we will explore why stars shine and how they produce energy steadily for millions or billions of years. Once a star has formed, it begins a long period of steady energy production. This is what makes stars shine, sometimes for billions of years without burning out quickly. At the center of a star is its core. Here, temperatures and pressures are extremely high. Under these conditions, atoms move rapidly and collide with great force. These collisions allow a process called nuclear fusion to occur. Nuclear fusion happens when light atoms join together to form heavier ones. In most stars, including our Sun, hydrogen atoms fuse to form helium. This process releases energy. That energy moves outward from the core and eventually escapes as light and heat. Fusion is not an explosion. It is a controlled, balanced process. The outward energy produced by fusion pushes against gravity, while gravity pulls inward. When these two forces balance, the star remains stable. This balance is why stars shine steadily, rather than all at once. If fusion produced too much energy, the star would expand and cool. If it produced too little, gravity would cause the star to contract and heat up. Over time, the star naturally settles into a stable state. The light we see from a star has travelled a long path. Energy created in the core can take thousands or even millions of years to reach the surface. Only then does it begin its journey through space toward planets and observers. This long journey smooths out variation. Sudden changes in the core are not felt immediately at the surface. As a result, stars shine with remarkable consistency. Different stars shine differently. Some are hotter and brighter, others are cooler and dimmer. These differences depend on mass, composition, and age. Despite these differences, the underlying process is the same. Fusion converts mass into energy according to simple physical laws. These laws apply everywhere in the universe. For someone listening quietly, this process can feel grounding. Stars do not need attention to continue shining. They do not adjust themselves constantly. They remain balanced through natural feedback. You do not need to visualize the core or the reactions. It is enough to know that stars shine because they are balanced systems. Energy flows steadily, without hurry. As you rest, this steady release of energy can be a calming thought. Light travels outward. balance is maintained. In the next part, we will look at the many different types of stars, how they vary in size, temperature and lifespan, while still following the same basic rules. Not all stars are the same. Even though they form and shine through similar processes, stars vary widely in size, temperature, brightness, and lifespan. These differences arise from one main factor: mass. A star's mass determines how strongly gravity pulls inward. More massive stars compress their cores more intensely. This leads to higher temperatures and faster nuclear fusion. Less massive stars fuse their fuel more slowly and remain cooler. Small stars, often called red dwarfs, are the most common type in the universe. They are cooler and dimmer than stars like the Sun. Because they burn their fuel slowly, they can shine for tens or even hundreds of billions of years. They change very little over long periods of time. Stars similar to the Sun are medium-sized and stable. They produce energy at a moderate rate and maintain balance for billions of years. Our Sun has been shining for about half of its expected lifespan and will continue steadily for billions more. Large stars behave differently. They are hotter, brighter, and more energetic. Their intense gravity causes fusion to occur at a much faster pace. As a result, they use up their fuel quickly, sometimes in only a few million years. Temperature affects color. Cooler stars appear red. Hotter stars appear blue or white. This color difference is not a surface feature, but a direct result of how energy is produced and released. Brightness can be misleading. Some stars appear bright because they are close. Others appear bright because they are truly powerful. Astronomers use careful measurements to distinguish between distance and actual energy output. Despite these differences, stars follow the same physical rules. Fusion behaves the same way in every core. Gravity acts consistently. Balance emerges naturally when forces oppose each other. This consistency allows scientists to group stars into categories. These categories help predict how stars will behave over time. They also allow astronomers to understand distant stars by comparing them to nearby ones. Stars do not choose their type. Their characteristics are set by initial conditions, how much material they formed from and how that material gathered. Once formed, a star's path is largely determined. For a resting listener, this can be a calming idea. Diversity does not imply chaos. Variation exists within structure. The universe allows many forms while remaining orderly. You do not need to remember the names or classifications. It is enough to know that stars differ, but they are not unpredictable. They follow slow, understandable patterns. As you continue to rest, you can let this idea fade into the background. Different paths, same rules, quiet variation within steady systems. In the next section, we'll look at how stars change over time, their life cycles, and how long-term processes shape their future. Stars do not remain exactly the same throughout their existence. Over very long periods of time, they change in predictable ways. These changes are called a star's life cycle. A star spends most of its life in a stable phase. During this time, it steadily converts hydrogen into helium in its core. Gravity pulls inward, energy pushes outward, and the two forces remain balanced. This phase can last for billions of years, depending on the star's mass. Eventually, the supply of hydrogen in the core begins to decrease. When this happens, the balance shifts slightly. The core contracts under gravity and becomes hotter. This change affects the outer layers of the star. For medium-sized stars like the Sun, this leads to a gradual expansion. The star becomes larger and cooler at the surface. Its light changes slowly over time. Nothing happens suddenly. More massive stars experience similar changes but on faster timescales. Their greater gravity causes more rapid shifts in temperature and structure. Even so, these changes still unfold over millions of years. Throughout a star's life, gravity remains the guiding force. It determines how material moves and how energy is produced. The star adjusts continuously, responding to internal changes in a calm, regulated way. Importantly, stars do not make abrupt decisions. They follow physical laws step by step. Each stage leads naturally into the next. There is no randomness in the process. This gradual evolution allows astronomers to study stars at different stages. By comparing many stars, scientists can reconstruct the full life cycle without watching a single star from beginning to end. Patterns emerge through observation and patience. For someone listening quietly, the life cycle of a star can feel reassuring. Change does not mean instability. It means slow adjustment within familiar rules. Stars are not fragile. They are resilient systems that adapt over long timescales. Their transformations are measured and steady. You do not need to imagine each stage clearly. It is enough to know that stars age gently. They respond to time without urgency. As you rest, this idea can mirror your own rhythm. Nothing needs to be immediate. Change can happen slowly without disruption. In the next section, we will look at what happens near the end of the star's life, how stars fade, transform, or leave behind dense remnants, all in calm accordance with physical laws. When a star reaches the later stages of its life, its behavior depends mostly on its mass. There is no single ending that applies to all stars. Instead, different paths unfold slowly, guided by the same physical laws that shape the star from the beginning. For smaller and medium-sized stars, the end is gentle. As fuel in the core becomes limited, the star sheds its outer layers gradually. These layers drift away into space, forming a faint cloud of gas. What remains is the dense core, which slowly cools over time. This remaining core is stable and quiet. It no longer produces energy through fusion. Instead, it releases stored heat slowly, fading over billions of years. There is no sudden collapse or disruption. More massive stars follow a different path. Their cores become dense enough to trigger more extreme changes. When fusion can no longer support the core against gravity, the structure rearranges rapidly. Even in these cases, the process follows strict physical rules. The result may be a very dense object left behind at the center. This object continues to exist long after the star itself has changed form. Surrounding space eventually settles and stability returns. Importantly, the death of a star is not the end of matter. Material released during this process becomes part of the surrounding environment. Gas and heavier elements spread into space, joining clouds where new stars may one day form. Nothing is wasted. This recycling is a natural part of cosmic balance. Stars form from existing material and return material when they change. The universe reuses its components without urgency or loss. For scientists, these endings provide valuable information. They reveal how matter behaves under extreme conditions. They also explain the origin of many elements found throughout space. For a listener at rest, this process can feel calm rather than dramatic. Endings do not mean disappearance. They mean transition. Stars do not resist change. They respond to it gradually according to physical limits. Their final stages are as structured as their beginnings. You do not need to picture dense cores or drifting clouds. It is enough to know that stars complete their cycles quietly. They leave behind order, not chaos. As you settle further, this idea can remain softly present. Change is part of continuity. nothing vanishes suddenly. In the next section, we will focus on one of the densest outcomes of stellar evolution, neutron stars, and how matter behaves when gravity becomes extremely strong. Some stars end their lives in a state that is difficult to imagine, but calm to describe. These are neutron stars, objects formed when gravity compresses matter to extraordinary density. A neutron star is created when the core of a very massive star collapses inward. During this collapse, the pressure becomes so intense that atoms are forced together. Electrons and protons combine, forming neutrons. The result is a core made almost entirely of tightly packed neutrons. Despite this extreme compression, neutron stars are not large. They're typically only about 20 kilometers across, yet within that small size they contain more mass than the Sun. This means their density is extremely high. To give a calm comparison, imagine a volume no larger than a city. Within that volume is packed the mass of a star. Matter behaves differently under such conditions, following rules that scientists continue to study. Gravity at the surface of a neutron star is very strong. It holds the object together firmly. Even so, the star remains stable. It does not collapse further unless it exceeds certain limits. Neutron stars often rotate steadily. They can spin many times per second, maintaining a regular rhythm. This motion is not chaotic. It is precise, governed by conservation of energy and momentum. Some neutron stars emit narrow beams of radiation as they rotate. When these beams sweep past Earth, they appear as regular pulses. These pulses are so consistent that they can be used as natural timekeepers. Again, extreme conditions produce reliable patterns. Despite their unusual nature, neutron stars are not violent by default. They are compact, stable remnants. After formation, they change very slowly. For scientists, neutron stars provide insight into how matter behaves at high density. They test theories under conditions that cannot be recreated on Earth. Yet even here, physical laws remain consistent. For someone resting, this idea can feel grounding. Even at extremes, the universe does not abandon order. Structure persists. You do not need to imagine the pressure or the density clearly. It is enough to know that matter can exist in many states. Each state follows predictable rules. As you continue to relax, you can let this idea settle. The universe accommodates both gentle processes and dense outcomes without conflict. In the next section, we will turn to another outcome of stellar evolution, black holes, and explain them calmly as regions of space shaped by gravity, rather than mysterious objects. Black holes are often described in dramatic ways, but scientifically, they are best understood calmly. They are not holes in space, and they are not objects moving through the universe. They are regions where gravity has become extremely strong. A black hole forms when a large amount of mass is concentrated into a very small region. This can happen at the end of the life of a very massive star. When gravity overwhelms all other forces, space around that region becomes deeply curved. The defining feature of a black hole is not what it looks like, but how gravity behaves near it. There is a boundary around a black hole called the event horizon. Once something crosses this boundary, it cannot return. Outside this boundary, gravity behaves normally. Importantly, black holes do not pull everything toward them indiscriminately. From a distance, their gravity acts just like the gravity of any other object with the same mass. Planets could, in theory, orbit a black hole just as they orbit a star. The difference appears only very close to the center. Black holes do not actively consume space around them. They grow only if material falls in. Most black holes are quiet, stable features of galaxies. They can exist for billions of years without significant change. At the centers of many galaxies, including the Milky Way, there is a very massive black hole. It influences the motion of nearby stars through gravity. Yet even here, the system remains orderly. Stars follow predictable paths. Black holes are important for understanding gravity and space-time. They show how matter and energy affect the structure of the universe. They do not represent a breakdown of physical laws, but a place where those laws reach their limits. For a resting listener, it can help to release the idea of black holes as threats. They are distant, rare, and governed by rules. They are not active dangers. You do not need to imagine darkness or falling. You can simply think of black holes as regions where gravity is concentrated. They are part of the universe's structure, not exceptions to it. As you relax, this understanding can remain gentle and factual. Even extreme gravity fits within a larger pattern of order. In the next section, we will step away from stars and their remnants and look at motion on a calmer scale, how orbits create balance and stability throughout the universe. Orbits are one of the universe's most stable patterns. They describe how objects move while remaining connected, guided by gravity and motion working together. An orbit happens when an object is pulled inward by gravity while also moving sideways. Instead of falling straight in, it follows a curved path. This balance between attraction and motion creates a stable loop through space. The object keeps moving, and the system remains intact. This pattern appears everywhere. Moons orbit planets, planets orbit stars, stars orbit the centers of galaxies, even galaxies orbit one another within larger groups. Orbits are not rigid tracks. They are flexible paths shaped by mass, distance, and speed. As long as these factors remain balanced, the orbit remains stable. Small changes usually lead to slow adjustments, not sudden collapse. One reason orbits are calming to study is their predictability. Once an orbit is established, it can last for extremely long periods. The Earth has followed roughly the same path around the Sun for billions of years. This consistency allows climates, seasons, and long-term stability. Orbits also prevent constant collision. Gravity draws objects together, but motion keeps them apart. This balance allows complex systems to exist without constant disruption. It is a quiet form of cooperation between forces. Scientists describe orbits using clear mathematical relationships. These relationships work the same way everywhere in the universe. They do not depend on location or scale. A small satellite and a distant galaxy follow the same principles. Importantly, orbits do not require control or correction. Once set in motion, they persist naturally. There is no central force adjusting paths moment by moment. The system maintains itself. For someone resting, this idea can be reassuring. Stability does not require effort. Balance can emerge naturally from simple conditions. You do not need to picture exact paths or angles. It is enough to know that motion and gravity create reliable patterns. These patterns allow the universe to remain structured without strain. As you continue to relax, you can let this image settle softly. Objects moving, held in place by balance rather than force. Motion without urgency. In the next section, we will explore how planets themselves form within these orbital systems, assembling slowly from disks of material around young stars. Planets form slowly, in much the same calm way that stars do. They do not appear fully formed. They assemble over long periods of time from material already present around young stars. After a star is born, a disk of gas and dust often remains around it. This disk is flat and rotating, shaped by gravity and motion. Within it, tiny particles move gently, occasionally colliding and sticking together. At first, these particles are extremely small, grains of dust, bits of ice, simple compounds. Over time, repeated contact allows them to grow. Small clumps become larger ones. This growth is gradual and uneven, guided by local conditions. As objects grow, gravity begins to play a stronger role. Larger bodies attract more material. This leads to a process where a few regions in the disk gather mass more efficiently than others. These regions slowly become the building blocks of planets. Temperature matters during this process. Closer to the star, heat prevents certain materials from solidifying. Farther away, cooler conditions allow ice and gas to remain stable. This difference helps explain why inner planets tend to be rocky, while outer planets are larger and richer in gas. Planet formation does not happen quickly. It can take tens of millions of years for a system to settle. During this time, objects may shift positions, merge, or be ejected from the system entirely. Even so, the overall process remains orderly. Once a planet reaches a stable orbit, change slows down. The system becomes quieter. The remaining debris is either absorbed, expelled, or settles into predictable paths. What remains is a stable arrangement of planets moving calmly around their star. This slow assembly explains why planetary systems differ from one another. Small differences early on can lead to different outcomes later. Despite this variation, the underlying process is the same everywhere. For someone listening quietly, this idea can feel reassuring. Complex systems do not require sudden creation. They emerge through accumulation and time. You do not need to imagine the collisions or disks clearly. It is enough to know that planets form through patience. Nothing is rushed. As you rest, this process can mirror your own slowing rhythm. Growth happens without urgency. Stability comes later. In the next section, we will explore why planets differ so much from one another, in size, composition, and temperature, even when they form around the same star. Even within a single planetary system, planets can be very different from one another. Some are small and rocky, others are large and rich in gas. These differences arise from a combination of location, material, and time. Distance from the star plays an important role. Close to a star, temperatures are higher. Only materials with high melting points can remain solid. This leads to the formation of rocky planets near the center of a system. Farther from the star, conditions are cooler. Ices and gases can remain stable. Planets forming in these regions can grow much larger because more material is available. This often results in gas-rich planets with thick atmospheres. Mass also matters. More massive planets can hold on to their atmospheres more effectively. Smaller planets may lose lighter gases over time. This difference shapes surface conditions and long-term evolution. Timing influences outcomes as well. If a planet forms early, it may capture more gas from the surrounding disk. If it forms later, less material may be available. Small changes in timing can lead to noticeable differences. Planetary motion adds another layer. Planets can migrate slowly within a system as they interact with the disk or with one another. These movements are gradual and often stabilize over time. They do not usually lead to chaos. Despite this variation, planetary systems tend toward stability. Orbits adjust until long-term balance is reached. Once settled, systems can remain unchanged for billions of years. For scientists, studying different planets helps reveal how physical processes operate under varying conditions. Each planet is a natural experiment. Together, they form a broader picture of planetary behavior. For a resting listener, the message is simple. Difference does not imply disorder. Variation exists within structure. You do not need to remember specific planet types. It is enough to know that planets reflect their environment. They are shaped by where and when they form. As you continue to relax, this idea can remain softly present. Conditions matter. Outcomes vary calmly. In the next section, we will shift from planets to something more abstract but equally steady. Time in the universe and how it behaves on large scales. Time in the universe moves forward in a steady, consistent way. It does not speed up or slow down without cause. On large scales, time provides a stable framework in which physical processes unfold. In everyday life, time feels personal and flexible. Moments can feel long or short depending on attention and emotion. In physics, time is measured more carefully. It is treated as a dimension, similar to space, that allows events to be ordered and compared. Across most of the universe, time behaves predictably. Clocks would tick at similar rates in similar conditions. Stars age, planets orbit, and galaxies evolve according to consistent timelines. Nothing skips ahead or falls behind unexpectedly. Very strong gravity can affect how time passes. Near massive objects, time moves slightly more slowly compared to regions with weaker gravity. This effect has been measured and confirmed, but it is usually very small. For most of the universe, time flows evenly. Because time is consistent, scientists can reconstruct history. They can calculate how long stars shine, how long galaxies take to form, and how the universe has changed. This allows predictions to be made calmly and reliably. Cosmic time operates on scales far larger than human experience. Millions or billions of years are common units. On these scales, change feels slow and continuous rather than dramatic. The universe is not rushed by time. For a resting listener, this can feel grounding. There is no pressure from cosmic time. Processes unfold when conditions allow. You do not need to imagine timelines or equations. It is enough to know that time provides stability. It allows order to emerge. As you settle further, this idea can rest quietly in the background. Time flows. Nothing needs to hurry. In the next section, we will look at how astronomers measure vast distances using light years, and why this unit helps make sense of cosmic scale. Distances in the universe are so large that familiar units stop being useful. Kilometers and miles become numbers too large to picture. To solve this, astronomers use a different measure, the light year. A light year is not a measure of time. It is a measure of distance. It describes how far light travels in 1 year as it moves through empty space. This distance is enormous, far beyond everyday scales. Using light years allows scientists to speak clearly about cosmic separation. Instead of listing long strings of zeros, they can describe distances in terms that relate directly to observation. Because light is how we see the universe, measuring distance through light makes practical sense. When we say a star is 5 light years away, we are saying its light has travelled for 5 years before reaching us. This means we're seeing the star as it was 5 years ago. Distance and time are linked through the motion of light. This connection is central to astronomy. Light years also help explain why space feels calm and quiet. Objects are separated by vast distances. Interactions take time. Nothing happens instantly across space. Even within a galaxy, stars are far apart. The nearest star system to our own is several light years away. Between stars, space is mostly empty. This emptiness contributes to long-term stability. For scientists, light years allow maps of the universe to be built gradually. They help compare nearby stars to distant galaxies. They provide a consistent scale that works across vast ranges. For a resting listener, the idea of light years can be soothing. It reminds us that space is spacious. There is room between things. You do not need to imagine the actual distance. It is enough to know that separation is natural in the universe. Events are not crowded. As you relax, this idea can remain quietly present. Light travels patiently. Distance allows calm. In the next section, we will explore one of the most important pieces of evidence about the early universe, a faint background signal that fills all of space. There is a faint signal that fills the entire universe. It comes from every direction, evenly and quietly. This signal is known as cosmic background radiation, and it provides one of the clearest pieces of evidence about the universe's early history. Long ago, the universe was much hotter and denser than it is now. Matter and energy were packed closely together. Light could not travel freely because it was constantly interacting with charged particles. Space was filled with a bright, uniform glow. As the universe expanded and cooled, conditions slowly changed. Eventually, atoms were able to form. When this happened, light could finally move freely through space. That light has been traveling ever since. Over billions of years, the expansion of the universe stretched this light. Its energy decreased. What was once intense radiation cooled into a very faint signal. Today, it is detectable only with sensitive instruments. This background radiation is nearly uniform in all directions. That uniformity tells scientists that the early universe was remarkably even. There were no large gaps or sharp boundaries. Small differences existed, but overall conditions were consistent. Those small differences mattered. Tiny variations in density became the seeds for galaxies and stars. Gravity slowly amplified these variations over time. From subtle unevenness, large structures eventually formed. The presence of this background radiation confirms several key ideas. It supports the age of the universe. It supports the idea of expansion. It shows that the universe has changed gradually rather than suddenly. Importantly, this radiation is not something we feel or see directly. It does not affect daily life. It exists quietly in the background, constant and stable. Its temperature changes extremely slowly over time. For scientists, cosmic background radiation acts like a reference point. It provides a baseline for understanding large-scale structure. It helps test theories and refine measurements. It is one of the calmest signals in all of science. For a resting listener, this idea can be comforting. The universe carries a memory of its early state. That memory is not loud or disruptive. It is steady and uniform. You do not need to imagine glowing space or early conditions. It is enough to know that the universe left behind a quiet trace of its beginnings. That trace still exists, unchanged in its basic form. As you relax, you can let this idea settle softly. The universe remembers calmly. Its past does not intrude. It simply remains present. In the next section, we will look at matter and energy, the two fundamental components used to describe everything that exists in the universe, from stars to empty space. Everything in the universe can be described using two broad concepts, matter and energy. These are not separate realms, but closely related aspects of physical reality. Together, they explain how the universe is structured and how it changes over time. Matter is anything that has mass and takes up space. Atoms, planets, stars, and galaxies are all forms of matter. Even very thin gas clouds and tiny particles count as matter. If something can be weighed, even indirectly, it belongs in this category. Energy, on the other hand, describes the ability to cause change. It can appear as motion, heat, light, or stored potential. Energy allows matter to move, interact, and transform. Without energy, matter would remain motionless and unchanged. In physics, matter and energy are deeply connected. Under certain conditions, matter can be converted into energy, and energy can behave like matter. This relationship is described by well-tested physical laws. It is not something that happens often in daily life, but it is common in stars. Inside stars, small amounts of matter are converted into energy through nuclear fusion. This energy then travels outward as light and heat. Over long periods of time, this process powers stars steadily and reliably. It is one of the most consistent sources of energy in the universe. Energy also exists in empty space. Light travels through regions with almost no matter at all. Fields and radiation can exist where particles are rare. This means the universe is never truly empty. Despite this complexity, the behavior of matter and energy is predictable. They follow conservation rules. Energy does not disappear. Matter is not lost. Both change form, but the total amount remains consistent. This consistency allows scientists to model the universe accurately. They can track how energy moves through systems. They can calculate how matter responds to forces. These calculations remain reliable across vast scales. For a resting listener, this idea can feel stabilizing. Nothing appears from nothing. Nothing vanishes without trace. Change happens through transformation, not loss. You do not need to remember equations or technical terms. It is enough to know that matter and energy work together. They create structure and motion calmly. As you continue to relax, you can let this idea settle. Forms may change, balance remains. In the next section, we will explore a kind of matter that does not emit light, dark matter, and how scientists know it exists through its gravitational effects rather than direct observation. Not all matter in the universe can be seen. In fact, most of it cannot. This unseen component is known as dark matter. Dark matter does not emit light. It does not reflect light. It does not absorb light in ways our instruments can detect. Because of this, it cannot be observed directly through telescopes. Scientists know dark matter exists because of gravity. When they observe how galaxies rotate, the visible matter is not enough to explain the motion. Stars at the edges of galaxies move faster than expected. Something unseen must be providing additional gravitational pull. This pattern appears again and again. In galaxy clusters, the motion of galaxies suggests far more mass than what can be seen. Light from distant objects bends as it passes through space, indicating extra gravity along the way. These observations are consistent across the universe. Dark matter behaves calmly. It does not clump tightly like ordinary matter. It forms large, diffuse structures that surround galaxies. These structures act like invisible frameworks, guiding how visible matter gathers. Without dark matter, galaxies might not form as they do. Stars and gas would disperse more easily. The universe would look smoother and less structured. Dark matter provides stability on large scales. Importantly, dark matter does not interact strongly with ordinary matter. It passes through space and even through planets without noticeable effect. It does not collide, heat up, or produce light. Its presence is felt only through gravity. Scientists continue to study dark matter carefully. They design experiments to detect it indirectly. So far, its exact nature remains unknown. This uncertainty is accepted calmly as part of ongoing exploration. For a resting listener, dark matter does not need to feel mysterious or unsettling. It is not a hidden threat. It is a quiet contributor to structure. You do not need to imagine invisible particles or complex theories. It is enough to know that gravity reveals what light cannot. Some things shape the universe without announcing themselves. As you relax, this idea can remain softly present. Not everything needs to be seen to have an effect. Stability can come from what is quiet. In the next section, we will look at another unseen influence, dark energy, and how it relates to the universe's continued expansion. While dark matter helps hold structures together, another unseen influence affects the universe on the largest scales. This influence is called dark energy. Dark energy is not something we can see or touch. Like dark matter, it does not emit light. But unlike dark matter, it does not pull matter together. Instead, it appears to be associated with the expansion of space itself. Astronomers discovered dark energy by observing very distant galaxies. They found that the expansion of the universe is not slowing down over time, as once expected. Instead, it is gradually accelerating. Something is counteracting gravity on the largest scales. Dark energy is the name given to this effect. It is not yet fully understood, and scientists describe it cautiously. What matters most is what it does, not what it is. It causes space to expand at an increasing rate over vast distances. This acceleration is extremely gentle. It does not affect galaxies, solar systems, or planets. Local gravity easily overcomes it. Dark energy becomes noticeable only when looking across billions of light years. Because of this, dark energy does not disturb daily life or familiar cosmic structures. Galaxies remain intact. Stars continue their orbits. Nothing nearby is being pulled apart. Dark energy acts evenly throughout space. It does not come from a single source or direction. Every region of space appears to be influenced in the same way. This uniformity keeps the universe smooth on large scales. Scientists include dark energy in their models because it improves accuracy. It helps explain observations without adding unnecessary complexity. As with many discoveries in science, understanding develops gradually. There is no rush to force an explanation. For a resting listener, dark energy does not need to feel unsettling. It is not an active force pressing in. It is a background effect, subtle and widespread. It works quietly over immense distances. You do not need to picture space stretching or accelerating. It is enough to know that expansion continues gently. The universe has room to grow. As you relax, this idea can remain distant and calm. Change happens far away, slowly and evenly. Nothing nearby is disturbed. In the next section, we will step back from unseen influences and look again at visible structure, how order emerges across the universe, creating patterns that repeat from small scales to large ones. When the universe is viewed as a whole, one of its most noticeable features is order. Despite its immense size, patterns repeat across many different scales. On small scales, atoms follow clear rules. Electrons move in predictable ways. Energy levels are stable. These patterns form the foundation of matter. On larger scales, the same idea continues. Planets follow regular orbits. Stars form in similar ways across different galaxies. Galaxies themselves arrange into clusters and long filaments, separated by wide regions of emptiness. This large-scale structure is not random. It emerges naturally from gravity acting over time. Small differences in density grow slowly. Matter gathers where gravity is slightly stronger, leaving space quieter elsewhere. Astronomers describe the universe as having a kind of texture, not smooth everywhere, but not chaotic either. There is repetition, spacing, and balance. These qualities remain consistent wherever we look. What makes this order calming is that it does not require direction or intention. No part of the universe is being guided moment by moment. The same physical laws apply everywhere, and order emerges on its own. Complexity grows from simplicity. This explains why distant regions of the universe look familiar. Stars behave like stars. Galaxies follow similar patterns. The same processes repeat across billions of light years. For scientists, this consistency allows understanding to build slowly. Observations from one region can inform knowledge about another. Patterns reduce uncertainty. They create reliability. For a listener at rest, this idea can feel reassuring. Vastness does not mean disorder. Large systems can be calm and predictable. You do not need to imagine the full structure of the universe. It is enough to know that repetition exists. The universe is not a collection of unrelated events. As you continue to relax, this sense of order can remain gently in the background. Structure does not require effort. It arises naturally over time. In the next section, we will explore another universal feature, motion, and why nothing in the universe is truly still, even when everything feels calm. Nothing in the universe is completely still. Even when something appears motionless, it is usually moving in ways that are not immediately noticeable. On Earth, motion is easy to see. Objects fall, water flows, clouds drift. In space, motion continues, but on much larger scales and over longer times. Because these movements are slow and steady, they can feel almost invisible. The Earth rotates on its axis. It also moves around the Sun. The Sun orbits the center of the Milky Way. The Milky Way itself moves through space relative to other galaxies. All of this motion happens continuously without interruption. Despite this constant movement, systems remain stable. Orbits repeat. Paths are maintained. Motion does not automatically lead to disruption. This stability comes from balance. For every motion, there is counteracting influence. Gravity, momentum, and distance work together to produce smooth trajectories rather than sudden changes. The result is motion that feels calm rather than chaotic. Even atoms are in motion. Particles vibrate, shift, and interact according to temperature and energy. At higher temperatures, motion increases. At lower temperatures, it slows, but it never fully stops. This universal motion is not a sign of restlessness. It is a natural state. The universe does not need to pause to remain stable. Movement and stability exist together. For scientists, motion provides information. By observing how things move, they can infer mass, distance, and force. Motion reveals structure rather than hiding it. For a resting listener, this idea can be comforting. Stillness does not require complete lack of motion. Calm can exist alongside gentle movement. You do not need to imagine all these motions happening at once. It is enough to know that movement is continuous and reliable. Nothing is rushing. As you relax, this can mirror your own experience. Breathing continues, the body adjusts. Rest does not mean stopping, it means settling into a steady rhythm. In the next section, we'll look at how the universe is governed by physical laws, simple rules that apply everywhere and allow this motion and stability to coexist. Everything we have described so far, stars, galaxies, motion, and change, follows a small set of physical laws. These laws are not instructions given to the universe. They are descriptions of how matter and energy behave consistently. Physical laws apply everywhere we can observe. They do not vary from place to place. Gravity works the same way in distant galaxies as it does near Earth. Light follows the same rules no matter how far it travels. This consistency is one of the most important discoveries in science. It allows astronomers to understand distant objects without visiting them. By studying nearby systems, scientists can make reliable conclusions about faraway ones. Patterns repeat. Physical laws are simple in form, even when their outcomes are complex. A small number of rules can produce a wide range of structures. Over time, these rules allow matter to organize itself naturally. No extra guidance is required. These laws do not react to attention. They do not change based on observation. They operate continuously, quietly, and predictably. The universe does not need to check its own behavior. Because the laws are stable, long-term structures can exist. Stars can shine for billions of years. Planets can maintain steady orbits. Galaxies can persist across cosmic time. This stability allows the universe to feel calm on large scales. Even though change occurs, it follows clear paths. Nothing happens without cause. Nothing unfolds randomly on average. For scientists, physical laws provide reassurance. They allow knowledge to accumulate rather than reset. Each discovery builds on previous ones. Understanding grows gradually. For a resting listener, this idea can be soothing. The universe does not behave unpredictably. It follows dependable patterns. You do not need to know the equations or details. It is enough to know that simple rules create reliable outcomes. Order does not require effort. As you settle further, this idea can remain quietly present. The universe is consistent. It does not surprise itself. In the next section, we will explore how change happens over very long timescales, and why cosmic change feels slow and steady rather than sudden. Change in the universe is real, but it is rarely fast. Most cosmic change happens over timescales so long that motion feels almost invisible. Stars take millions of years to form. They shine for billions of years. Galaxies evolve slowly as stars are born, age, and fade. Even the expansion of the universe unfolds gently when viewed moment by moment. This slowness is not accidental. It is a natural result of scale. Large systems have a great deal of inertia. They do not respond instantly to small influences. Because of this, the universe tends toward continuity rather than disruption. Structures persist, paths repeat, adjustments happen gradually. On human timescales, this can be difficult to appreciate. Our lives move quickly by comparison. But when we look outward, the pace changes. The universe does not rush. Long timescales allow balance to emerge. Small disturbances fade. Large trends become clear. Stability becomes the default state rather than the exception. For scientists, this makes prediction possible. If change was sudden and frequent, understanding would be difficult. Instead, the universe provides time. Time to observe, measure, and confirm. Knowledge accumulates slowly, just like cosmic structure. For a listener at rest, this idea can feel calming. Nothing important needs to happen right now. The universe is comfortable with waiting. You do not need to imagine billions of years passing. It is enough to know that change does not demand urgency. Processes unfold when conditions allow. As you relax, this sense of extended time can soften attention. There is room to pause. There is no schedule to meet. In the next section, we will widen our perspective slightly and explore scale. Why the universe feels abstract to human senses, and how science bridges that gap gently and carefully. The universe operates on scales far beyond what human senses evolved to understand. Distances are vast, times are long, and masses are enormous. Because of this, the universe can feel abstract or difficult to picture, even when described accurately. Human perception is tuned for nearby objects and short durations. We are comfortable with meters, minutes, and familiar sizes. When those units are extended by millions or billions, intuition no longer works the same way. This is not a failure of understanding, but a natural limit of perception. Science addresses this gently, without forcing imagination. Instead of asking us to picture extreme scales directly, it uses comparison and measurement. Numbers, ratios, and consistent units allow ideas to be handled calmly and precisely. Understanding becomes possible without visualization. For example, astronomers do not try to imagine the full width of a galaxy. They measure rotation speeds, brightness, and distance. From these values, structure emerges without needing mental images. Knowledge replaces intuition. This approach keeps science grounded. It avoids exaggeration and drama. It allows facts to remain stable even when scales are extreme. The universe does not need to feel familiar to be understood. For a resting listener, this can be reassuring. You do not need to grasp everything fully. Partial understanding is enough. Accuracy does not require vivid imagination. You can allow scale to remain distant and abstract. The universe does not demand that you picture it clearly. It only requires that its rules be followed. As you continue to rest, this idea can release effort. Understanding can be quiet. Clarity can exist without detail. In the next section, we will look at how humans observe the universe, how tools extend perception without changing the calm nature of what is being observed. Humans do not observe the universe directly with their senses alone. Instead, we use tools to extend perception gently and precisely. Telescopes collect light that eyes cannot gather on their own. Detectors measure wavelengths beyond visible color. Instruments record signals too faint, too distant, or too slow for direct awareness. These tools do not change the universe. They simply allow us to notice it. Observation in science is careful and patient. Data is collected over long periods. Measurements are repeated. Results are compared across many locations and times. This method reduces uncertainty. It avoids rushing to conclusions. Understanding builds slowly, based on consistency rather than impression. Importantly, observation does not disturb most cosmic systems. Stars do not change because they are observed. Galaxies continue their motion regardless of attention. The universe remains steady. This distance between observer and observed is calming. There is no requirement to influence or interact. We are free to watch without intervention. Knowledge does not demand control. For scientists, observation is about listening rather than forcing answers. Signals are received, patterns are identified, explanations emerge gradually. For a listener at rest, this idea can feel grounding. You're not required to act or respond. Understanding can come through quiet attention alone. You do not need to imagine telescopes or instruments clearly. It is enough to know that observation is gentle. The universe reveals itself without pressure. As you continue to relax, this approach can mirror your own state. Awareness without effort. Presence without demand. In the next section, we will step further back in time and consider the universe before humans, how cosmic processes unfolded long before any observer existed. The universe existed for a very long time before humans appeared. Stars formed, galaxies evolved, and space expanded without any observers to record it. These processes did not require awareness or interpretation to occur. For billions of years, matter followed physical laws quietly. Gravity gathered gas into stars. Stars lived out their life cycles. Galaxies slowly changed shape and position. Nothing waited to be noticed. Nothing paused for explanation. The universe functioned continuously, guided by the same rules that still apply today. This long history matters because it shows that cosmic processes are independent of observers. The universe does not behave differently when it's watched. Its stability does not depend on attention. It unfolds according to physical conditions alone. Evidence of this early universe remains visible. Light from ancient stars still reaches us. Background radiation carries information from early stages of expansion. Structures we see today reflect processes that began long before life existed. For scientists, this continuity allows reconstruction. By observing present conditions, they can infer past events. Time connects moments without interruption. History is embedded in structure. For a resting listener, this idea can feel grounding. The universe does not demand participation. It does not rely on awareness to continue. You do not need to imagine ancient scenes or dramatic beginnings. It is enough to know that the universe has always been in motion. Change did not begin with observation. As you relax, this can ease effort. Understanding does not require involvement. Things can simply be as they are. In the next section, we will explore why the universe feels calm on average, how stability and predictability dominate, even though rare extremes exist. When we hear about the universe, dramatic events often receive the most attention. Explosions, collisions, and extreme objects stand out. But these events are rare. On average, the universe is remarkably stable and predictable. Most regions of space are quiet. Stars follow long, steady orbits. Galaxies change slowly. Large structures persist for billions of years without disruption. This stability comes from balance. Forces like gravity and motion counteract one another. When systems reach equilibrium, they tend to remain there. Small disturbances usually fade rather than grow. Predictability is what allows science to work. If the universe behaved randomly, patterns would be difficult to detect. Instead, similar conditions produce similar outcomes. This consistency holds across vast distances and long times. Even rare extreme events follow rules. They do not break physical laws. They simply occur under uncommon conditions. Once they pass, stability returns. For a resting listener, this idea can be reassuring. The universe is not constantly on the edge of change. Calm is the default state. You do not need to focus on rare events. Most of the universe is steady, quiet, and balanced. It continues without urgency. As you relax, this sense of predictability can settle gently. Things behave as expected. There is no surprise waiting. In the next section, we will look at cycles and repetition, how many cosmic processes repeat in reliable ways, reinforcing long-term calm. Many processes in the universe repeat. They follow cycles that unfold reliably over time, reinforcing stability rather than change. Planets complete their orbits and begin again. Stars rotate steadily. Galaxies continue their slow motion through space. These cycles do not require intervention. They persist naturally once established. On smaller scales, repetition is just as common. Atoms transition between energy states. Particles interact in predictable ways. Even light follows consistent paths as it travels. Cycles help systems remain balanced. They allow energy to move without being lost. They prevent buildup or collapse. Through repetition, systems regulate themselves. Astronomers rely on these cycles to understand the universe. Regular motion allows measurement. Predictable timing allows comparison. Patterns make long-term observation possible. Repetition does not mean sameness. Each cycle may differ slightly. Small variations accumulate slowly. Change emerges gently, not abruptly. For a resting listener, cycles can feel comforting. They suggest continuity. They suggest return. Nothing is required to be new all the time. You do not need to track the details of any cycle. It is enough to know that repetition exists. The universe revisits familiar states. As you continue to relax, this idea can soften attention. Motion repeats. Balance renews itself. In the next section, we will reflect lightly on our place within these vast systems, not philosophically, but as a simple fact of being part of a larger structure. Within all this scale, motion, and structure, there is also a simple fact. We are part of the universe we observe. The same physical laws that shape galaxies also shape atoms in the body. The same gravity that guides stars influences the Earth. There is no separation between local experience and cosmic process. They are different scales of the same system. This does not require meaning or interpretation. It is simply a description of connection. Matter follows rules wherever it exists. Energy behaves consistently, whether near or far. Humans did not introduce complexity into the universe. Complexity was already present. Life emerged under specific conditions within existing structure. Observation came later. For science, this perspective is grounding. It avoids exaggeration. It avoids isolation. It places human activity within a broader ongoing process. For a resting listener, this idea can feel settling. There is no need to feel small or large. There is only placement. You are located within a system that continues calmly. You do not need to think about purpose or outcome. It is enough to know that participation is passive. The universe does not require a response. As you relax, this understanding can remain light and factual. You are here. The universe continues. In the next section, we will begin to return toward rest, revisiting the night sky and the act of observing without effort. As we begin to slow the pace further, it helps to return to something familiar. The night sky is often the first place people encounter the universe directly. When you look up, the view is simple. Points of light against darkness, no labels, no explanations required, just steady presence. The sky does not reveal scale immediately. It does not announce distance or age. It offers quiet signals, arriving patiently as light. Observation does not demand effort. For most of human history, the night sky changed very little from one lifetime to the next. Stars rose and set. Patterns repeated. This regularity made the sky a source of orientation and calm. Even now, with scientific understanding, the experience remains the same. You do not need to calculate distances or identify objects. You can simply notice that light arrives, that motion continues. For a resting listener, the night sky represents continuity. It is there whether or not it is observed. It does not react to attention. It remains stable. You do not need to imagine yourself outdoors or looking upward. The idea alone is enough, a steady view, a quiet system. As this section settles, we will move closer to rest itself, emphasizing that the universe continues without urgency and that rest does not interrupt anything. The universe continues whether we are watching or resting. Stars keep shining. Galaxies keep moving. Space continues to expand slowly and evenly. Nothing pauses when attention fades. Nothing requires effort to maintain. Processes unfold at their own pace, guided by stable laws that do not hurry. This continuity is one of the universe's most calming features. There is no deadline written into cosmic motion. Change happens, but it does not demand immediacy. Rest does not interrupt anything important. On large scales, the universe is comfortable with waiting. It allows time for balance to settle. It allows structures to persist. It does not rush toward outcomes. For a resting listener, this can feel reassuring. You're not holding anything together. You're not required to stay alert. Everything continues on its own. You do not need to imagine events unfolding elsewhere. It is enough to know they proceed quietly. Motion without urgency, change without pressure. As you let this idea settle, attention can soften further. Awareness can loosen. Nothing needs to be followed or remembered. In the next section, we will prepare for sleep by returning once more to calm motion, allowing the mind to rest within steady continuation. Even as everything continues to move, there is room for rest. Motion in the universe does not require awareness. It does not need monitoring or response. Stars shine without effort. Planets remain in orbit without correction. Galaxies persist without attention. Movement and rest coexist naturally. This is an important idea to hold gently. Rest does not mean stopping the universe. It means allowing it to continue without participation. Nothing is lost when attention fades. Your own rest follows the same pattern. Breathing continues. The body maintains balance. Processes carry on quietly in the background. There is no need to stay focused on facts or ideas. They do not need to be held in place. Understanding can dissolve into background awareness. Knowledge does not disappear when attention softens. As this section settles, the universe can remain exactly as it is, stable, predictable. Unconcerned with observation, you can allow thoughts to slow, you can allow details to fade. Nothing important depends on staying awake. In the final section, we will close gently, returning to the simple idea that everything flows steadily, and that rest fits naturally within that motion. The universe moves continuously, guided by simple rules. Stars form and shine, galaxies drift. Space expands quietly. Nothing needs to be completed, nothing needs to be resolved. Motion does not require direction. Change does not require urgency. You are free to rest within this steady flow. There is no need to follow the universe any further. It will continue on its own. Everything flows. Sleep in that motion.